Hello, my name is Paul Hargrove, and on behalf of myself and my co-authors, Dan Bonacea, Colin McLean, and Daniel Waters, welcome to this 5-minute video in which I will briefly describe each of the 7 panels of GasNDX memory kinds, support for device memory in PGAS programming models. GasNDX is a communications middleware library for partitioned global address space programming models, or PGAS models for short. GasNDX is one component of our work in the Pagoda project at Lawrence Berkeley National Lab. This diagram depicts our ecosystem, in which GasDX runs over several different low-level network APIs, providing portable communications interfaces to various PGAS programming models, which in turn support exascale applications. PGAS models represent an alternative to the predominant MPI for writing distributed applications. To be a practical alternative to MPI, a PGAS model should match or exceed MPI in terms of both productivity and performance. While each individual PGAS model approaches productivity differently, those which use GasDX depend on it for communications performance. This panel presents performance of remote memory access, also known as RMA, get and put operations on 4 systems which together span 2 network technologies and 3 MPI implementations. The bar chart to the left shows GasDX latency for 8-byte RMA operations to be better than MPI by between 5 and 55%. The line plots to the right show GasDX RMA operations for a range of sizes reaching saturation bandwidth sooner at transfer sizes typically 2x or 4x smaller than required to reach saturation using MPI. For reference, the bandwidth plots also show the performance of MPI message passing. In summary, this panel demonstrates that compared to MPI, both RMA and message passing, GasDX RMA delivers comparable or superior performance on a variety of systems. We believe this is possible due to the excellent semantic match between GasDX RMA and the capabilities of modern HPC networks, and not simply the result of quality of implementation issues. This panel presents the problem statement and the approach we have taken to solve it. Stated briefly, the problem is to enable performance of RMA operations to and from GPU memory that is comparable to the host memory performance in the previous panel. The poster identifies 3 key challenges, though one of these is addressed by support provided by the relevant network and GPU vendors. The other 2 challenges are related to efficiency and extensibility of the design. The bullets outline a solution and how it addresses these 2 challenges. In particular, the GasDX object model has been extended with the addition of a memory kind as an abstraction of non-host memory without any semantics which would preclude other sorts of accelerators or even storage. This extension to the object model enables efficient implementation by ensuring the host versus device distinction for memory at both ends of an RMA transfer are decidable from the communication endpoints used, without the need for any dynamic queries using the address arguments. This design removes one of the most significant implementation challenges faced by CUDA-aware MPIs. As I alluded to in describing the previous panel, part of the solution is provided by the relevant hardware vendors. A technology known as GPU Direct RDMA, or GDR for short, enables the GPU and the network interface to communicate as peers over the PCI Express bus. This allows communication libraries such as GasDX and CUDA-aware MPI implementations to offload GPU memory transfers to the network hardware, removing the host CPU and memory from the critical path for the transfer itself. This panel is the first of 3 presenting performance results used to evaluate the memory kinds implementation. The plot in this panel shows flood bandwidth performance of the OLCF Summit system, where the hardware supports GDR. The results shown are for RDMA get transfers from a remote GPU to a local GPU using a micro benchmark written in UPC++, another of our group's projects. The lowest and highest series show the improvement due to the use of GasNDX's memory kinds as compared to the prior approach using CUDA memcopy and host memory buffers at both ends of the transfer. The other series shows the performance of an analogous MPI benchmark using CUDA-enabled IBM Spectrum MPI. As with the earlier results for host memory RMA, GasNet is able to saturate the network using smaller transfers than required when using MPI. This panel shows a before and after performance comparison for the Legion programming system, another PGAS model using GasNDX for communication, on an NVIDIA DGX-1 system. These plots demonstrate that updates made to Legion's Realm runtime library to utilize GasNDX memory kinds yielded improvements in latency and bandwidth of RMA transfers involving various combinations of host and GPU memories. This panel completes the evaluation of GasNDX memory kinds performance with a figure extracted from a study of an application kernel on OLCF Summit. In this study, a COCO-spaced heat conduction example code was modified to replace a Halo exchange implemented using MPI message passing with one using UPC++ and RMA. The IBM Spectrum MPI implementation is CUDA-aware, and the UPC++ build uses GasNDX memory kinds. The study observed that the UPC++ version of the code scales better and provides more uniform performance than the original MPI code. As noted in the poster, more complete details will be presented in the PolyATM workshop on Friday morning. The authors express our thanks to those listed on screen and to you for your interest in our work.